Hello, my name is John Tonner. I'm the Executive Director of the American Membrane Technology Association, and AMTA is an organization which promotes membrane technology, particularly in water and wastewater use. And today we're here to record another one in our series of Chats with the Pioneers. And with me today I have Bruce Biltoff and Warren Johnson, who were early employees in a little company from Australia called Memcor, which became a key technology provider in the microfiltration and ultrafiltration segment of the industry. And I'd like to ask you, Bruce, if you could introduce yourself first and give us your background and how you wound up working in the membrane industry.
Yeah, thanks, John, and thanks ever so much for the opportunity to be interviewed today. So I'm a mechanical engineer by training, and I joined what was then known as Memtech Limited, the holding company for Memcor, in 1985. I was 26 at the time, so a graduate engineer. That said, I'd taken the long way around to become an engineer and had been working since I was 16 in mechanical engineering at a technical level, then completing my tertiary degree. So I was pretty well equipped as a young engineer and looking for an opportunity of something new and exciting. And I answered a small ad. I'd just moved to Sydney the year before from Brisbane in Queensland. Saw an ad for a development engineer for this exciting new technology company, and I got hooked pretty quickly from there. So I stayed with the Memcor business in its various generations for 37 years, and just left the company in August of 2022. So what got me interested was a startup in membrane technology. There's a couple of key sort of images of that in the original prospectus and the first annual report for Memtech. And this was a business formed out of research at the University of New South Wales in Sydney, Australia. So the uni had got interested in membrane technology in the 70s, and under Professors Chris Fell and Tony Fain, together with some contributions from a researcher from France, Michel Lefebvre, and also a gentleman by the name of Peter Farrell. In Australia, Baxter Healthcare, which is a US corporation, was pretty significant in the healthcare business, and the uni decided to buy dialysis cartridges from Baxter to use for them to insert their research membranes in. So basically it was a way for them to encapsulate their membrane. The then head of Baxter in APAC, Dennis Hanley, noticed that these guys were buying dialysis membranes at a pretty steep price, and thought, well, he had an interest in what was going on. I think Dennis also had in his mind an intention even then that he wanted to start his own business at some point and come out of the large corporate. He said that in his own words, that he was really looking for something different. So he visited, got excited. They started a JV between Baxter, the university's commercial arm, Unisearch, and formed Memtech Laboratories. And then Dennis engineered a way to essentially acquire that business and form Memtech Limited. So Memtech Laboratories was formed in 81. In 82, 83, they acquired that business and then went on the road to investors. And in 1984, Memtech Limited was listed on the Australian Stock Exchange with 4 employees. So there was Dennis Hanley, Mike Quinn, Doug Ford, and Bill Anderson, an engineer out of the uni. And basically Dennis, he was a Harvard MBA graduate, a Baker Scholar, so a really high-achieving gentleman. And he used the 2 networks. He used his Baxter network and his Harvard network to sort of build the team that would go on to start Memtech Limited. I came in as a mechanical engineer in what is ultimately very much a chemistry and chemical engineering business, but every company needs mechanical engineers, so that's normal.
I wholeheartedly agree.
So my job was my job initially was in fact to design an extruder, so which I did, and then some changes happened, and I ended up in the box seat designing both the products and the equipment. And this was a whirlwind. We were doing so many things. We hired a sales team, and from a company perspective, it expanded quite quickly. So we were regarded as the first listing on the ASX that really didn't have a product. It was very much just a core technology. That flipped from the research at the uni almost instantly. So that was flat sheet research. The product very quickly was hollow fibres, which in the very initial sense were outsourced fibres. And probably the most significant contribution, certainly that Doug made, was what we call the gas backwash, which really defined a lot of what we did for pretty much the next decade. And that was where we inject high pressure air through the membrane to basically help with the removal of solids. And we had to engineer products around that. So it was a very simple handmade membrane module initially, and then we got into manifolding those modules together pretty much right from the get-go, and that was something that I worked on quite a bit. We had this sales team doing a bunch of things. We had already started pretty quickly in the US, in Chicago area actually at the time. And we later then started in Europe, in the UK and Germany, and in Japan, all within the 80s. So essentially we became a global business quite rapidly. But the sales activities were a pretty wide net. Where could you, excluding healthcare, where industrially or even potentially in water and wastewater treatment could you apply the product? So if you looked at our install base by the end of the 80s, it was a spread across a range of applications. But in around 87, and I'll let Warren speak to when he came on board, and then the work in particular in the wastewater and integrity testing, we had one success in 86 at Keystone in Colorado to remove Giardia from one of the resort water supplies on the ski mountain for Giardia removal. And Dennis had made a visit to the UK and visited Mogden Farm, which, if you know, is a very big sewage treatment works off the M3, I think, is southwest of London. And he just saw this and thought, you know, we could do this so much better. We could shrink this. We could break it up into distributed pieces. And really, he then went on a big pitch to push membranes for both water and in particular for wastewater recycling. And then so we were growing a bit. We were probably up to, so when I joined in 85, there were maybe 10 employees. By 87, there's a picture of all of us. It's maybe 60 or so employees. So pretty rapid from that initial start. And more younger engineers were coming on board, which is where Warren comes into the picture. So I'm going to let him speak a little bit.
Yeah, thanks Bruce, and thanks John for the opportunity. I started really, my interest in membranes started when I was at university. I did my degree in chemical engineering at the University of New South Wales. And so Chris Fell and Tony Fain, who Bruce mentioned, were two of my professors in my course, and they introduced us to membranes, and I had some knowledge of who Memtech were, but at the time I had a scholarship with the Electricity Commission, so I took a job with them when I left, which was interestingly turned out to be quite a good opportunity. I actually worked in construction on some new power stations that were zero discharge, so I got to work with all sorts of water technologies, including RO, which was my first exposure to membranes. They were operating what was then one of the largest RO systems in the Southern Hemisphere. So I got to see that being built, worked on commissioning it, and then ran that for a while. So that was good experience. And then I saw an advertisement for Memtech. I thought, well, I know these guys, this looks interesting work. I was looking for a new challenge, and I applied for the job. I got the job, and I started actually working on a project which was a joint collaboration between the University of New South Wales and Memtech, exploring the combination of bioreactors and membranes. So very early concept of membrane bioreactors. I did that for a little while and sort of grew things from there, but I started being involved in sort of things that were coming through the door. As Bruce said, we had lots of different applications, and I think in many respects it was a product trying to find an application. And so I got to filter all sorts of stuff that came through the door. You know, people would bring weird and wonderful product in, and I'd go and run some filtration trials to see what would happen, which was quite an interesting experience. And you got to do a lot of different things with, some of them worked really well, some of them just didn't work at all. So that was good fun. But I think really what I started to do then was get more involved in pilot trialing and developing other technologies. I continued with Memtech. I'll come back to some of the things that we did, but I continued with them for 21 years, finally becoming the global director for R&D for Memcore products. And then I left to join another startup company, which was a startup company that Dennis Hanley was running in the solar industry. So that was another opportunity I took up for a few years and explored that, and then eventually came back to the water industry, and I'm currently working for a company called Aquacell that does water recycling systems for commercial office buildings and residential blocks and off-grid developments and the like. Again, using membrane technology. So membranes have been a part of my career from pretty much the very start.
It's in both your DNAs, it sounds like.
Yeah.
You're both a couple of short timers. You don't hang around at a company very long, in and out.
Yeah.
You mentioned a couple of things there that caught my ear. One of them was you worked on these zero liquid discharge power plants. Was the RO system a pre-concentrator to a thermal brine concentrator?
No, it was actually on the cooling circuit. So it was to remove salt from the cooling water system. So normally you do blowdown, and they didn't have anywhere to blow down, so they had to take the salts out
Cool.
with an RO.
Right.
So that was interesting.
You mentioned the MBRs, because one of the things when I was looking back over some of the history of the company, some of the first projects that I guess there was a lot of press about were possibly cleaning up the water outfalls in the Sydney area. And I think one of them you got to work on a pilot scale with an MBR ahead of the MF. Is that right?
I'll take a step back from it. I think we, in the days of trying to find where this thing had its best application, and as Bruce said, there was some early recognition that maybe wastewater was an opportunity. We actually did some crazy stuff. We filtered raw sewage to see what would happen when you put that through a membrane. And surprisingly, we pretty much rejected all bacteria and viruses that we could measure, which came as quite a surprise. So all of a sudden we thought, wow, this is a technology that can disinfect raw sewage. Right. And so we started thinking about, maybe it could work on outfalls, maybe there were other applications for that in the wastewater industry. And we managed to work with Sydney Water, which was the major water and wastewater company or utility within Sydney, and we were able to get a project up which was built in Blackheath in the Blue Mountains, just west of Sydney, and that was a tertiary filtration system on a very old trickling filter wastewater plant. And what we wanted to do there was try and demonstrate what membranes could do. Looking particularly at disinfection and filtration of a secondary effluent. For us, that project was critical because when you're working with wastewater and you're looking for disinfection, it's one of those few wastewater feeds where you've got such a high concentration of pathogens and bacteria in the feed, it's very easy to see if you've got good integrity or not, because if you don't, you'll find it in the filtrate. And sure enough, when we started it up, we were finding bacteria coming through, and we didn't know where it was coming from. Is this a factor of scale up? Is it membrane integrity? Is it just because bacteria grow in pipes? We didn't really know. So we had to figure that out, and through that process we developed things like the sonic analysis, where you could identify where the leaks in modules were coming from. We did autopsy techniques to break down any modules that we knew were leaking and try and find where the source of the problem was. We developed all sorts of integrity monitoring techniques, pressure decay testing and diffusive airflow testing, or DAF testing, which were extremely sensitive integrity monitoring techniques, which were able to detect integrity at sort of 1 part in 10 to the 6, which was what we needed to be able to monitor and control a plant like that. Eventually, we figured out what was going on. It was a manufacturing issue. We fixed it. Guys like Bill Beck and Humphrey Drummond and others spent a weekend just integrity testing a bunch of modules and getting them back onto the plant. And then we ran 21 straight weeks without a single coliform coming through the system.
In a weekend, they managed to do that.
Well, there's a lot of modules to test, so they spent some time.
A lot to achieve in a weekend.
So at the end of that, we figured out, okay, we can do this. This can be scaled, and you can use it.
Wow. I mean, Bruce, you mentioned that when you came on board, one of your first projects was an extruder, but you also mentioned flat sheet and procuring fiber material. When did everything get honed in on extruding and proprietary materials?
Pretty quickly. It was really a matter of progressing to be able to make the product ourselves. So in that period prior to really getting manufacturing up, proving it out, we had to source membrane. So Baxter, was already a business that we were connected with, and I think that's how we found the pathway to have a membrane in our hands without actually having to be able to make it. But that was pretty short. That was maybe 2 years, and we were pretty much into making our own product. Certainly the facility at Windsor, which is west of Sydney, which is where we still make, or where Memcor still makes its product today, that was opened in 1987, and that's been making membranes pretty much all the way through. So yeah, it was just a matter of getting that up and running. The thing that so out of what Warren was referring to was that in that decision of Dennis's that this is what we want to do, part of it was the unproven bit. You have to demonstrate this. So in the US, Dennis recruited, and which is pretty amazing, Dr. Vince Oliveri. So Vince was a very well-known epidemiologist in the research community here, sitting in a very nice job in a very distinguished university. He actually joined Memtech. He was so excited about what this could do that he was prepared to come on board. And Vince helped to present the work, and we had to do it all in the US as well as in Australia. The thing that the work in Australia did for us is it gave us the confidence that we could do this. We still had to demonstrate it here in the US. So a lot of pilot work done with various research bodies here in the United States. But the other element was the scale. So the scale was starting from a very small base. We didn't really have a reference point. I mean, we were starting, my world, the brief was, here's the membrane, make the product. And then we made a decision we would scale it up. Still didn't have a particular reference point. We scaled by an order of magnitude, which seemed like a pretty decent jump, and it was, but it was still ultimately, we've gone further than that since then. But as we got up towards the end of the 80s and we were building this plant in Blackheath, it's a really nice little plant, great design, incorporates various things that we have today in design, but it was still a little bit small. So in 89, we did a design program to design the M10 membrane module, which in its format still speaks to products today that are made by Memcor, and still a huge number of our customers have membranes built around that platform. And we designed that over 6 months. A gentleman named Mike Selby and I used to go to a design agency that helped us with the broader sort of design layout of the product. And every Friday afternoon we'd go down, we'd crack a few beers and we'd brainstorm. Then we'd go back to our day jobs during the week and we'd think about things ourselves and then go back each Friday. And within 6 months, that whole technology platform was designed, including the membrane module, the housings, the arrays, how to hang them, how to remove them, the whole system. It was pretty good. And it actually ended up with a DuPont polymer being the one that was the only one that would withstand the duty that we were going to ask it to do. But yeah, it was a pretty successful program. Pre-CAD, all done, in the old school method, and then converted to computer later on.
So when you were working on that module design, was the fibre choice, the fibre properties, dimensions, everything fixed, and it was the rest of the module, or were you optimizing everything?
No, in that instance, the fibre itself was not changing. So we set a length and bundle size constraint, but everything around it we moved around and were changing. We did elect, as people would know, MEMCore modules are what we call a submodule with a housing, and partly there are probably two aspects to why we did that. One is when Warren mentions about we learnt this experience, how do you figure out what's going on here if you can't see the membrane? So that was a desirable thing, to be able to have a membrane that you could physically look at. But the other thing was that at that point the business was doing a range of activities, including wine and juice and to some extent beer, but food and beverage things. So from a design viewpoint, the product needed to be sanitary, and also when you solvent cement housings, you have the risk of leachables coming out, which would taint a wine, for example. So we were desirous of not having any solvent joints in the product, and between those things, we elected to make it a reusable housing with a membrane inside it, and that's pretty much what we've stuck with as MEMCore ever since for the pressurised products. And right now it's probably perfect from a sustainability viewpoint because we're not throwing away. We're only, ultimately it's only the core bit that gets replaced.
Over the last few questions, you've both mentioned a few things about pilot testing and being able to monitor and detect what's going on. And I think, Warren, you mentioned integrity testing. Can you tell us how your ideas and concepts for that developed?
Yeah, sure. It became very important for us, and I think it's been very important for the industry as a whole to be successful. Our early systems, even from the various early systems, had a pressure hold test, which was basically pressurising the lumen side and looking to see if it held pressure based on bubble point theory. And it was fairly crude, but quite effective. I mean, if it held pressure, it was good. If the pressure dropped, it wasn't so good. If it dropped quick, it was much worse. So it was a little bit like that. But we realised that was going to change with the size of the system. We needed to be able to understand what was going on. Some other people at Memtech, Humphrey Drummond and others, looked at what became known as a diffusive airflow test, which is a version of a pressure hold test, but much more sensitive. It's able to detect probably up to about 10 to the 6 integrity compared to, say, maybe 1 part in 10 to the 4 for a pressure hold test. So it became very, very, very sensitive. But we realised quite early on that there must be a relationship between the integrity test pressure and the decay rate versus the rate at which it'll leak across the membrane. Right. And therefore the rate at which solids may bypass the membrane, or in other words, the integrity or the log removal capability of the system. So I sat down one day and started to try and work through the simple formulas to relate the flow of air through the membrane under test conditions to that which you would get from fluid flow under filtration conditions. And you can relate those two things relatively easily. And particularly if you make some assumptions, we're able to derive some equations which told us the equivalent log removal of a system based on its pressure decay rate or its diffusive airflow rate. And that allowed us to actually quantify this in a very practical way. So we then did a lot of work on proving that in the laboratory, running some trials to demonstrate that it actually did work. And we ultimately captured that in the ASTM method for integrity testing of low pressure membranes, which was based on that. And that whole concept of being able to relate the test results to the log removal is the basis of the EPA filtration guidance manual, membrane filtration guidance manual approach to integrity monitoring as well. So it became, for us, a very important thing for the industry, not having developed all of that, particularly in the wastewater environment where you have enough bacteria to verify significant challenges. You could then take that across into the water industry where you couldn't do that. You don't have a high enough turbidity or a high enough particle load or a high enough pathogen load in the feed water in most cases to be able to monitor integrity directly. And these integrity test methods allowed us to quantify what the log removals are, even though you couldn't measure a change in the filtrate quality. Yeah. And that became very important to being able to develop confidence that this technology could be applied in the water industry, and also help get the confidence we needed with the regulators and the health department authorities to be confident to support membranes and to permit those systems.
So this is reaching the start of the 90s. And so what we've done is satisfy ourselves that we can be a disinfection barrier for water treatment and also wastewater, tertiary wastewater treatment. But we're at that point in a very chicken and egg sort of situation, which is technology looks great. I mean, very easy to get people excited. You show them a turbid feed water and that, you know, glass of water is what you see on the other side of the membrane. People loved it till they saw the price, and then and they sort of went, ooh. You know. So we, you know, we needed to get the cost down, but to get the cost down, you've got to sell product to get volume, etc. So it is a chicken and egg problem. I actually personally left Australia and moved to the UK to work for Memcor in the UK. It was at the time that the water industry had just been privatised, so the 10 PLCs were formed in the UK. I went on the road basically doing exactly that. Everyone got excited until they saw the price. So it was a slog. A guy by the name of Rob Whale left Australia about the same time and became the sales lead here in the US. And, you know, we were working pretty hard, getting some small systems, but the big things that helped us were the surface water treatment rule. So together with the fact that we could now have a basis for how to demonstrate the extra pathogen rejection that a membrane would provide, the Clean Water Act, which I think provided the funding to then execute some projects. And of course, it was amplified by the Milwaukee incident in 1993. So our first real significant success was with San Jose Water at Saratoga on their Congress Springs feed, which is a source that they treated annually with DE filters, but had a very narrow bandwidth of turbidity tolerance, I think 5 NTU. We lifted that to 250 NTU, and we installed within 6 months from the second half of 93 into the start of 1994, 5 MGD plant using the CMF technology that we designed in 1990, and that really sort of set the scene. In the meantime, Dennis had said, you know, this is just the best thing, the world's going to take off. So the share price had you know, got quite excited, but then not much had happened. So it started to dip again, but that allowed us the opportunity, the guys here in the US and to some extent out of Australia as well, to lay out designs for standard plants. So they did a lot of work to cookie cutter how to engineer these plants, and when things really started to move, we were pretty well set up to execute a whole number of projects in the US in the mid 90s and into the second half of the 90s.
Yeah, I think that's a really key point about the surface water treatment rule, because up until then we still felt that the wastewater market was where we make the difference. We can disinfect stuff, you know, and this is where it's going to have its biggest impact. But I think the surface water treatment rule and the success of projects like Saratoga and others turned our attention to the drinking water market, particularly in the US. And so for a while, that's where most of our focus moved. And so the drinking water market is really where we put our energies and efforts from that point. And then came back a little bit later, back again to saying, okay, we want to go back and explore the early work we began in wastewater and looking at MBRs.
Yeah, we did a project in Australia in 1994 at the Eraring Power Station, so that's north of Sydney. And one of the things that, you know, in the municipal world, it is hard to get customers to go first, and that's for good reason. I mean, this is a pretty conservative space with a significant responsibility and risk attached. So when you find clients who are prepared to jump first, you go with them. And the Eraring Power Station managed between them and the municipality locally to take tertiary effluent, and we installed a plant to essentially recover that water as boiler feed water for the power station instead of building a significantly expensive outfall for a relatively small plant. So we took 100% of the flow through a dual membrane process. So this was the first real commercial opportunity to tie MF with RO, and that's been a hugely successful plant. That was actually with CA membranes. So at that point, that was or around the time we were really learning that TFCRO would actually survive having a residual chloramine running through the process, because the key challenge in that space is how do you stop, biofilm regrowth and various fouling issues from coming up. And that work sort of was just happening, but at that time that plant went in with more conventional, so to speak, RO membrane in that application. And yeah, that's still running today, a highly successful plant. It actually somewhat launched the interest in membranes in China. So we used to host a lot of delegations from around the world, and from that basis of that plant, the use of recycled wastewater for power stations in China was pretty much mandated within a few years after that. And now, of course, China has an enormous membrane market, a lot of which steered from that.
Yeah, I think at the same time we were starting to explore membranes pre-RO at Water Factory 21, which would have been the early 90s.
Started about the same time.
Yeah. Yep. So we tested some of the very early iterations of the Memtech modules, the smaller 1 and 2 square metre modules there. And later we tested the larger systems, the systems that Bruce is talking about, the current format. But then we eventually tested the submerged membrane system, and that's what was ultimately installed there. So over a course of 8 or 9 years, we tested every iteration of the technology at Water Factory 21, and eventually installed the system there, which is still one of the largest, I think, in the world. Quite a significant project, that one. We worked with guys like Mehul Patel, Greg Leslie and others. Harry Ridgway, back in those days, was doing a lot of work there. And I remember even, I think it was Dick Sudak, who was the guy who was doing some work. I turned up there one day and we were running the pilot trials, and they'd been dosing chlorine ahead of the membrane, ahead of our membrane, before it even got to the RO. And of course, in those days, chlorine and polypropylene membranes were not a good mix. But they were successfully doing this, and not only that, the downstream membranes, even thin film composite membranes on the RO system, were seeing chlorine go through them as well, which was something we'd never seen before. And I think, and Dick believed it could work, and he was right. It did work, and it was largely due to the formation of chloramines and the nature of the organics that are present, that it actually did work. And that's really the basis of what was actually installed. And still today, people will dose chloramines into RO and give you a much longer life than was expected. So that became a fairly significant standard.
Yeah, I mean, that's a famous campus to be associated with as well, Water Factory 21.
Yeah, so, speaking about early adopters, I mean, Water Factory and Orange County themselves were prepared to let anyone come in and try the technology, and they were looking for something better than their lime clarification process, and they saw this was an opportunity, but we had to scale it a fair bit, and we then, as we went towards the project, as Warren alluded to, we flipped from pressurised to submerged, and I remember, the pitch made and the board, because when they make their mind up, it actually then gets a bit hard to change things. So we did have to say, look, this is going to work better. We've worked out that from a scale standpoint, the submerged process that we've developed gives you a better design, and that's the way it went. Yeah.
Do you think that's still true, that the larger the project tends to favour submerged?
Well, interestingly, and you know, we're one of the few manufacturers who since that period ended up in all three platforms, so pressurised, submerged and MBR. And you leverage from each. The key thing that submerged gave us was scale at the time, but we had shortcomings in pressurised that wouldn't let us do that. But we turned that around. So we actually ended up scaling pressurised even more so than submerged in some of the very big diesel plants. But today, I'd probably say in a simple analysis, you generally start with pressurised and then pick submerged if it suited the particular application. Mainly the reason being that membranes today are much higher performance, and having that bit of extra pressure does extract the full what the membrane itself can give you, and probably also from a sort of construction approach, typically, you know, bringing in kit that you simply drop on the ground is a little bit easier to work with. Submerged plants, once they're built, are fantastic. They're really, really nice plants. So we love having customers who like to build a submerged process, but probably today there's a bit more of a favouritism to pressurised in the market.
Right. Looking back from today or closer to today, in high performance membranes, you said, what are the key differentiators that brought that performance out, you think, over the years?
Well, let me start by saying there is no one simple way to do this. So at the end of the day, you're always trading something against another thing. So anyone who says their product can do it all is, you know, probably not to be entirely believed. But I guess the main thing is that in the way that majority of membranes are made today, in processes that allow you to formulate a membrane that does give you that mix of properties. So it gives you high hydrophilicity. I mean, UF, you know, is a tighter membrane, but it actually outperforms an MF membrane for the most part when you formulate it right, and you get the bonus of having a slightly tighter cutoff to go with it. But yeah, it's that ability to tune both the active surface together with the physical properties, and that the original membrane that we had, there wasn't, and there isn't. We still make that product today. There isn't the ability to do that. So it's the chemistry bit that's really changed things, and that'll keep. I think that will keep happening now. That's it's not dissimilar to what happens in RO. A lot of the differentiation performance is around the core chemistry of the product.
Yeah, to expand on that a little bit too, I think particularly in the earlier days when we were fairly standardised on the membrane itself, most of the energy was into process stuff. So how do you operate this thing? How do you keep the surface clean? How do you get the solids out? How do you clean the thing back? Those were the things that were significant. And I think that's probably why you had more diversity in the types of systems that hit the market compared to, say, an RO system, where in an RO system the feed is fairly well defined. It doesn't vary much. There's an SDI you need to hit, and you have to hit that. And then all the focus was on the membrane side once the module configurations had been figured out, and we ended up with the spiral wound systems as the dominant product. And I think these days there's a lot more of those two those two things coming together, with the membrane technology itself and the chemistry of the membrane combined with the processes to get the most optimal system.
So one aspect that we haven't chatted about so far is the energy consumption. So we were proving out the pathogen rejection, knew that to reduce cost we had to sell product, but in that sort of life cycle cost analysis, energy is a significant component. So when the business first started, what we called Memcore CMF was cross-flow microfiltration. That was the established way to run a membrane process, which is to pass the feed over the membrane, scour the membrane surface with feed stream and recirculate that. So those early years included a lot of design, in particular for some of the industrial and food and beverage applications, designing to run cross-flow. As we progressed to municipal, we realised, you've got to treat water at cents per kilolitre here, or cents per gallon, this isn't going to cut it. So we actually went cold turkey. We just literally switched it off and started running in dead-end filtration, direct filtration, and found to our surprise it wasn't too bad. It ran pretty well. And so when we did the Blackheath project, if you ever see a picture of that, there's a big tank in the background. Probably doesn't need to be a tank, but it absolutely proved the point. This was running under gravity head, and the process went, worked fine and has stayed that way ever since. Interestingly, in the iteration since then, all of those three technologies have dropped down in their energy consumption, and they're actually all pretty similar. Even MBR is quite similar to pressurised and submerged in terms of energy consumption. It's a significant advancement. We would have been probably about 1 kilowatt hour per kilolitre in the early days. It got down to about 0.4 when we did Blackheath, and now we're down 0.07, something like that. So it's a real change.
So on the subject of energy consumption, managing defouling obviously is a key component on that. And one of the things that I don't think we've talked about much that I think was one of the initial aspects of the IP was the introduction of air, or I think the patents might even have talked about other gases, right, as a backwash. We haven't talked much about that, and how much effort did you guys put into optimizing the frequency, the duration, or
only a little bit.
Only a little, but I mean, understanding the airflow. You mentioned earlier for integrity testing, understanding airflow in the forward direction, but the capability to handle higher flows in the reverse.
He can talk about the process, and I'll talk about the engineering of the equipment to cope with this thing.
Why don't you tell us a bit about that then, Warren?
Yeah, okay. So as Bruce started out by explaining, the original technology used the gas backwash, which is pressurizing the modules to 90 psi and then dropping the pressure very rapidly. It was an extremely effective way to get gas across the membrane surface, lift solids off, and then to scour it. And we did a lot of research running pilot trials, comparing units side by side, looking to see which elements of that process were the most effective and and what length the steps should be, what pressure should it go to, how fast does the pressure have to drop. All of those parameters to try and get the most out of it. Eventually learning a little bit more about the way that the module worked, we recognised that the stage where you sweep water across the surface and have the air flowing through the membrane was significant. It wasn't until a bit later that we started to explore other ways of introducing air, because one of the downsides of that method is that it's quite energy intensive, but also it's also a very effective method of getting air into the module. But we looked at other ways of doing it, and one of our research engineers, Fufeng Zha, started exploring ways of bringing the air in externally into those modules, and we found that we could do that relatively successfully, and we started developing modules that used external aeration, and then we started looking at immersing those modules in water and drawing the filtrate through without using a pressurized system, but using the same method of aerating it, which ultimately led to the CS product. And then we took those same concepts in the membrane bioreactor environment for the MBR products that came from that. One of the downsides of a pressurized gas backwash is that it's limited to relatively large pore sizes, because you're not going to get the gas through a membrane that's very fine pores. The bubble point's too high. So to do all that we wanted to do with membrane chemistry, we needed another way to do it. So there's various drivers for it: energy efficiency, the ability to run the system in a submerged configuration and to get away from the gas backwash, to allow us to use different types of membranes was core, and Fufeng did a lot of work in helping us to get through those ideas and develop some of the products that we have today.
So we were very wedded to this gas backwash for a long time. We even had to develop fast analysis tools to allow us to do what we call a snapshot, which was to get the operating parameters across this sequence, and we would look at that down to milliseconds and think, oh, is that going to make a difference? Is that making it? It's science of its own. And the valves, so this was 6 bar, so 100 psi almost of air in a plastic housing. So we had to engineer the parts to cope with this happening every 20 minutes. The air bit was every 20 minutes once, but the other consequence of blowing all this air through what is essentially a hydrophobic membrane is that when it's particularly new and clean, it actually just basically dries it, and suddenly nothing goes through the membrane. So, oh, what's happened here? So we developed what we call the re-wet sequence, which was basically to squeeze the water back onto the membrane. And so generally the backwash was the backwash sequence plus 2 of these cycles. So for every backwash, 3 times we went up to 100 psi and back down to 0. So we had to have these plastic components that would cope with roughly 1 million cycles of doing that within their lifetime. So there was a lot of work involved in that, and we had to have actuated valves that would actually run alongside that. So Keystone, to their credit, did a huge amount of work. I think we improved their product enormously because we had to, they had to get it to cope with all of this. The irony of which, as Warren said, was as we went into the submerged environment, it really was not going to work because you can't, you don't want all this air back on the suction side of your filtration pump. You can't squeeze the membrane because there's no housing to squeeze it. So we had to change the backwash. And ironically, we found that it wasn't the main thing that made the backwash work. So the submerged process changed, and we then flipped that back to pressurized later on when that went to the UF membrane. Shortly after, we took what we learned in submerged and translated that back to pressurized. And and the process changed quite a bit as a result of that.
Was this the birth of CEB, or chemically enhanced backwash?
That came, well, there's another, you can let someone else talk to the history of that. The point there, you may realise that in membrane plants in the US, the general design was 30-day CIP interval, which is purely a creation here in the US by some engineers and operators that said, I really don't want to be doing clean more than once a month. And it's stuck ever since. So the workaround, if you wanted to do more cleaning, was do this short cycle clean. And it wasn't us so much that got into that space. It was some of our competition who were actually struggling to hit the 30 days at the time and thought, oh gosh, how are we going to work around this? As it turns out, it is actually appropriate for PVDF. When you have membranes running pretty flat out, provided that's a stable process, it is absolutely fine to run the process that way. You extract, the biggest value component in the process is still the membranes. So your membrane inventory, does significantly drive the cost of the whole life cost. So things you can do to trim the size of the plant will always help from an overall cost perspective, albeit at the risk of lifting the process risk profile, but it definitely saves money.
So I think you mentioned that basically the Cadot patent decision led to a sort of commoditization of spiral wound membranes and the ability to, with minimal performance change, to shift from one manufacturer to another. But you guys created a market where your competitors' modules were all different sizes. And one of the more recent things to try and accommodate that is a universal rack, which seems to be focused on fitting the module in it. But I wonder if you could talk about, about all the other differences. All these flux rates are totally different, backwash rates.
So it's interesting about the cycle of things. So we were into manifolding modules pretty early on. It's fair to say that that if you're a salesman in any business, you sell the features of what you're taking to the customer. So ironically, some of the things we introduced, which others might have criticised in their sales pitch for many years, later on they turned around doing very similar things. So you've always got to, go in with your eyes wide open when you listen to some of that pitch. But we, as we went through to the current generation of pressurised product, you will notice that each of the manufacturers' products are getting to look a bit similar, and there's a few reasons for that. One is simply that as technologies evolve, things do gravitate towards what is somewhat optimal. Also, you've got to keep your mind to what the market is doing. You can sit right out, if you look at the B10 permeator, it's right out left field of all the spiral wounds. Really hard to hold your position in that when you're like that as a freestanding business. So if you go too far away from match racing, you run the risk that you just get left behind. Take the large RO elements, a little bit of some of that history there too. So we at the same time, we still valued the manifolding approach to shrink footprint. So when the current L40 CP2 process was designed, we worked hard to accommodate both avenues. So that product, if you see it in a working plant with the full manifolded arrangement, it's very elegant, looks nice, very compact. But the membrane module itself can actually come out and go into a completely universal arrangement as well. And so we knew that if we stayed too far left field, that was a risk, and I think it's worked quite well actually, because it allows us to do both things. There's also a little bit of things going ex-patent, not that necessarily of itself has driven much of that, but sometimes that allows designs to get similar. I mean, in RO, that is essentially the reason why they're all the same, is that there was they didn't have to actually do their own thing. That pretty much opened that space up to one design anyway.
Yeah, and I think it's definitely true that in the early days there was pressure from a lot of the engineering firms to try and standardise, because it made sense that you could do something like they'd done in the RO industry and have multiple competitors that all could bid the same product, that could all go into a system that they could design. But I think, I personally pushed back quite strongly on that as best I could, because I felt like at that stage, so much of the know-how was not around just putting a module on a block somewhere, but it was about how you operate the system. How do you backwash it? How do you clean it? And there were differences, and significant differences in the marketplace on how that was done. And I think until all of that got sorted out, moving toward a standard product was just never going to be effective. I think that's starting to change a little bit more so now. But
it is a highly empirical process. It's not, RO, you can run your sizing on the water chemistry, and there are some physical constraints, but it's much more defined. Very highly empirical with MF and UF processes. So your process knowledge is pretty key. And yes, there are three elements to development. One is the membrane, the second is the sort of physical product, and the other is the process. And that's still the case today. How you run it is still a key element of getting the best performance out of these products.
We've talked a little bit about MF, UF, and MF or UF. Can you talk to us a little bit about the evolution of your products, and both from a technology perspective and maybe as to how the end users with the applications perceived the performance differences, if any?
Yeah, I think in the early days there were no other competitors out there, so we were selling what we were making at the time, which was a microfiltration product. As other competitors came on, they had products which they were calling ultrafiltration, and when you actually boiled it down, the differences were not that great. And we did recognise that there was partly a marketing thing to be dealt with there. Microfiltration is one thing, ultrafiltration, that's got to be better, right? So we had a lot of challenges in the marketplace, helping people to realise that the differences weren't that significant when you get down to it, especially when you consider that a lot of the rejection happens on the fouling layer, and the membrane becomes more of a substrate than it is a filter. And so it wasn't as critical as the market was perceiving. But that said, there was still a demand to try and increase things like virus removal, particularly in drinking water applications. So we still had a driver to develop tighter and tighter membranes for those purposes, which we subsequently done to some degree of success. But I think in those days it was really just trying to handle this marketing issue of how do you differentiate these products. And I think MF at that stage was considered larger pore size. We needed MF for the gas backwash. Ultimately, we developed smaller and smaller pore sizes, partly to tackle the virus removal requirements that we were looking for in drinking water systems. And we also found we could improve performance in other ways as well, particularly as we modified the membrane chemistry, and those finer pore sizes worked quite effectively. So for all those reasons, we did ultimately move to finer and finer pore sizes. But if you look at the membrane spectrum, it is a spectrum, and it's very hard to say this is microfiltration, this is ultrafiltration. They overlap so much, and hence, rather than the market trying to get sound like they were favouring one technology over the other, it just kind of adopted MF/UF to cover everything, and it kind of hung around for a long, long time before anyone could agree on which of those two it should be. So.
Yeah, I mean, I think that the transition in terms of manufacturing gave us the bandwidth to optimise performance. So you can get more hydrophilicity in the formulations that are used in the UF products today. So you get UF as part of that. You can't really make an MF membrane like that. And notwithstanding that it's a tighter membrane, because it has a thinner active layer, it runs better than the MF membrane will, which has much less, if any, asymmetry. So the market, to some degree, wanted it. Probably the primary initial driver was chlorine. We could see that we were standing out alone. Once you have, some competition running the alternative in there, we had to pretty much have that option available. So we needed to have a chlorine-tolerant membrane as part of that, and then the need for virus rejection has become more prominent. It was never an issue in the US until pretty recently, and it's a little bit more prominent now. But in particular in our home market, small market, but it was a significant requirement on the wastewater side to actually have some virus rejection in a reuse plant through the low pressure membrane stage. So PVDF was good for that. But we're still making PP today. So that's 3.5 decades later. Still goes pretty fine, but almost no new project would use a PP membrane.
Interestingly, even on those early wastewater jobs, the polypropylene membranes did a great job of rejecting viruses.
Yeah. Well, one of the things that happened there is, of course, there's a difference between what the process does in operation and how you demonstrate it to a regulator. So the way that you have to demonstrate it is to run clean water challenge tests, and that's not what happens in a wastewater environment where virus particles are attached to larger particles. So we get excellent virus rejection in practice, but it counts for naught because you actually have to do this, a drinking water type test, which requires the membrane to be tight in terms of its pore size to get rejection. So yeah, it's a bit of a quirk of how things are done. I would also say that there's been a huge evolution in development for MEMCOR on the membranes themselves. We've had probably a few periods where it didn't quite live up to what we wanted or needed, but to the credit of the team in Windsor, the product today is really very, very solid, and there's a lot of know-how in that development process. In terms of the membrane chemistry, but also the tools to prove that the membrane will do what we want it to do. They do a fantastic job.
When Singapore PUB came up with their new water projects, what was the reaction to that, and what maybe you could tell us about the technologies that you took into those programs.
So Blackheath preceded that. We did a second project in Sydney at the Cronulla Sewage Treatment Works using the M10 technology that was part funded by Sydney Water. And then Singapore was getting serious about recycling, and we got into the pilot program at Biltoff, and then ultimately were successful then as US Filter, so we'll come to that part soon, to provide the dual membrane process for the demonstration scale at Biltoff. So that was in around 2000. And from there, in multiple projects in Singapore in terms of both new water and on the drinking water and even desal sides as well. So that's been a long association and a very successful one. But that demo plant shut down many years ago, but Kranji new water plant was built in around 2003, and that is still operating today. I think that plant has a life expectancy now that Truss water reclamation plant will start up in a few years, but it's been a very successful new water install. So starting with pressurised, that also transitioned to submerged for Kranji, and then the Changi new water plant, the Changi number 1, that uses the CP.
You mentioned the ownership. That was a US Filter at that phase. So
let's talk a little bit about that.
yeah.
So I guess so we joined, and maybe this is an opportunity to mention the naming a bit. So Memtech Limited was the name of the company that started, standing pretty logically for membrane technology. Doug Ford apparently is credited with coming up with the naming idea. So shortly after the business started, and we set up operations in the US and the UK and Europe, and then later Japan. We ran into some naming issues in the US. You would know the Memtech with K, tubular membranes became a sister company at one point. And also in the UK, there was a small business in Wales, I think, called Memtech with an H, CH. And so using Memtech as a product name outside of Australia was a little bit problematic. So the business in the US was Memtech North America Corporation. So from that, Memcore was a short form for that name, and that was the product name that we elected to use, and ultimately became how everyone would know us pretty much. You know, they wouldn't even realise that it was called Memtech today, probably. So from those 4 people, we grew through the mid-80s. Fortuitously, in 1987, Dennis had gone to the share market and had a fully underwritten $100 million capital raising in process when the stock market essentially took a huge dip in October of 1987. As that was fully underwritten, the funds came, and from that we acquired Filtrite and Fluid Dynamics, 2 divisions out of it's escaping me the name right now. The bowling lane company that
Brunswick.
Yes, Brunswick Corporation. So we acquired those 2 divisions, and that actually made us, you know, really very much a filtration technology company. I mean, those guys were very clever, and it was great to bring that together. We did some more acquisitions going into the 90s. Things were travelling quite well. We had that sort of wait period to get the Memcore market growing in the early 90s, but by and large, if you look at the financial results for Memtech Limited, 20% CAGR from late 80s right through to the mid 90s, starting to get noticed in the US market, and around a similar time, early 90s, US Filter was formed. And if you look at a US Filter annual report, whilst Memtech was growing at 20%, they were cracking at 120%. The management of Memtech just didn't see this coming. And we were one of the only hostile takeovers that US Filter made. And unfortunately, well, actually, it's not so much unfortunately. It was unfortunate for Dennis. It was his dream of Memtech, and once we were acquired, he pretty much, he bowed out and went to do other things, part of which Warren got involved with. But for us, we were pretty wedded to the technology. So you're either in or you're out. And so we were in, and that was fine. And that was exciting. So US Filter, as you know, that's another story. But interestingly, one of our potential white knights was Culligan, which literally got acquired, I think, about a month or two later anyway. So even if we thought that was going to save us, it didn't happen. That was an exciting time. And we then became part of Vivendi, Veolia, Siemens, Evoca, and now DuPont. And I would say that, when we talk about the technology, so the starting period was all the Memtech stuff, but in terms of the broader growth and the real heavy lifting of developing all three platforms, that's happened under the ownership of each of those corporations. So they have supported and invested significantly in Memcore. So there was no let up, and I think we were always, the interesting part of what was going on in terms of all the different divisions inside the corporation. But it did narrow our focus. So one of the things that happened was that we joined the municipal segment of US Filter. So that really narrowed our world down. The other pieces we were doing in other sectors pretty much dried up. The other divisions of Memtech became what was called FSG, Filtration and Separations Group, which then eventually was sold to Paul Corporation. So all of those other pieces ended up inside Paul. And we became a municipal water and wastewater focused activity.
That was a pretty concise summary of a topic that
I've lived through all of this.
I think a lot of people find it very confusing as to how that, but it definitely sounds like consistently the owners knew they were onto something.
Yeah, and I mean, they absolutely did, and they were, I mean, we had, Andy Seidel, Frank Fershing, all those guys. They always loved coming down to see what we were doing. They thought it was great, so they certainly did the right thing by Memcore in terms of where we went.
An interesting anecdote about the influence that you guys had in creating a segment of an industry is that at the Smithsonian Institution, there is a box of 27 of your old product catalogues.
Really?
That's got to mean something. You should go there and find that out. But someone took notice at the Smithsonian, so your work is there, along with work of NASA and other people like that.
So as we went out of the 90s into the 2000s, we had really had established a market. And then it was about scaling, and reaching a broader geography. The other thing was that, so the main applications were water treatment and wastewater treatment, but the one to come off the back of that was desalination as well in terms of pre-treatment. But before I get to that, on the sort of wastewater treatment side, we were scaling things. We had, Orange County finally went to construction of the groundwater remediation plant. That was a huge project. There's probably too many schemes to mention directly, but each of these projects, really built out the know-how and the scaling. The UK market. So when I was in the UK at the start of the 90s, there wasn't really a driver for membrane technology from a regulatory viewpoint. But as you may recall, post the Milwaukee incident, the decision was made that the directors of a PLC would be directly liable should they, cause a similar incident in the UK. So that really, amped up the vibe. And speaking of AMP, and the asset management plans that they would run on a 5-year cycle then started to include significant membrane projects. And we had tremendous success. Pete Rogers ran that business for many years in the UK. I think we built about 60 significant municipal plants in the UK alone for water treatment under those investment cycles. But the drivers on the wastewater and water side was pathogen rejection. For desal, it's a little bit different. Most desal plants, virtually all, some today do have no requirement for a pathogen rejection, unless you'll see schemes now. Singapore would include it, partly in Australia, where there's some risk of contamination of the seawater source. They would take advantage of low pressure membranes as pre-treatment. But by and large, it's an economic equation to flip from a historical conventional treatment. But we felt in coming up, so in the second half of the noughties in Australia, we were going through what was called the Millennium Drought. It was a 10-year drought. We were in a deep crisis on water supply, so significant reuse projects engineered by all of the main firms from here in the US were installed, but also desal started to happen. So initially Perth 1, then I think the Gold Coast, Sydney, and then as that was happening, we weren't ready for the first ones, but when Perth 2, being a Southern Seawater desal plant, and Adelaide came up, and also Victoria, we felt the technology was at a point where it would scale and be competitive. And and that proved to be the case. So we were successful with SSDP and with Adelaide, and they're two of the largest, amongst the largest desal plants in the world. But that's a different space. It's still a different space in terms of why you would use a low pressure membrane, and for people in the industry would be well aware, there's a lot of debate around that, because part of the pitch is to not use a coagulant, allow your wash waters to go out with the brine stream, don't have a lot of movement of chemicals and stuff, but of course that means you're living with the soluble organics that are in the raw water, and so biofouling can potentially be a challenge. But one of those plants is pressurised and one is submerged, which is another interesting comparison. And a few years after we built them, I went at each plant. The operators would say to me, "Why did we get this one and they got that one?" And so yeah. But ultimately, you've got to listen to your customer. That's part of how that happened.
What was the first plant, capacity-wise, you think, ever that had the Memcor brand name on it, and what's the biggest one? I mean, what was that growth and capacity?
The scaling is pretty tremendous, yeah. Actually. So that original membrane module was 2 square metres of membrane. We had this quirk. We actually pitched it the other way around. I don't know why we did that, but we did the calculation on the ID, which was before I turned up. So we spent years calling them M1s and M10s and saying,
gave you a higher flux.
So yeah, saying they were 10 square metres, and the market saying, this is not right. So anyway, we had to turn them around. So it was 2 square metres. The scaling is probably 2 orders of magnitude, but the product, I mean, when we did the M10, I could never have conceived that we would go from a design that was actually 60 modules in its concept, pretty quickly went to 120, but also in terms of the ultimate scale, the largest process unit using that sort of broad configuration has 960, nearly 1,000 membrane modules, treats 10 MGD in one process unit, and that's at Binning at the Southern Seawater desal plant. So that would be the largest by volume, which is about 220 or so MGD of UF capacity going on to the RO. The largest today, the largest for water is probably somewhat smaller, probably more around the the 80 MGD mark, but on MBR, so the evolution for us for MBR is had been a little bit tortured. So in amongst that pigeonholing in the municipal side of US filter, someone in their wisdom a little bit further on decided that not only would we do that, we would actually separate the MBR activity from the other parts of MEMCO and put that in the wastewater dedicated group out of Walkinshaw. And I think that actually did help significantly, but at the same time it also hindered. So we didn't need competition to have a few constraints in terms of trying to get on top of everything we needed to do in developing MBR. But I think ultimately the success is there, and today, most recently the business was successful with both the first and second stages of the Truss water reclamation plant, which is roughly 200 MGD of MBR capacity. So we're doing all three platforms at pretty much the same scale, and the learnings apply from one to the other. You learn, you're always looking at, if you do something here, how would it, how does it translate? And I think that's one of the things we significantly have brought to low pressure membrane.
So from a 2 square meter module to a couple of hundred MGD in a few decades, yeah.
Never have envisaged
Or even 1 square metre before that, wasn't it? And then we doubled the length of it.
Yeah, but it was, the surface was 2. So yeah, but it was, it's incredible.
Guys, maybe you could take a minute or so to run through some of the well-known names in the industry that are MEMCOR alumni.
Yeah, so look, from that original Fab, what we call the Fab Four, so Dennis, Mike, Doug Ford and Bill Anderson, things grew quite a lot. So in Dennis's network, Dr. Clint Kopp joined the company from Baxter. Clint's been recognised by AMTA for his contribution to both RO and to MEMCOR and MF membranes. We have a bunch of people who have been part of the business for nearly as long as I have, in back perhaps some less visible roles. A gentleman named of James McMahon has been the guy who's done the mechanical engineering that I injected upon him for nearly 4 decades. The research team that Warren was part of, he mentioned Dr. Fifeng Zhar, who's a significant contributor to MBR and the backwash processes. And here in the US, when we kicked off, Rob Whale came across from Australia. Rob was instrumental in getting the sales activities started. But probably, I guess, something that I found really inspiring is, I guess, the two aspects. One is looking at these highly credentialed, more senior people, but also our undergrads who came through and are now, a number of who are embedded in the industry. And maybe Warren can explain a little bit of the background to how that worked.
Yeah, I think having had that tie with the University of New South Wales, particularly going back to the early days, the university introduced a program called the Co-op Scheme, where they created scholarships for students to work in industry for part of their course. And Memtech, we were then recognised the opportunities that presented and started actively funding the students through that program. And we ended up funding, I don't know, must be something like 50 or so students at different times.
Yeah.
Some of those students have continued on with MEMCOR over the years, and some of them have gone on to other businesses as well. And coming through, what we did is sponsor those students to come through, and they'd spend 6 months of the year working with an industry company, in this case with MEMCOR. And so we bring them into the R&D team. And in R&D is one of the great places to start your career, because you're exposed to the technology at the basic level, and you're running pilot trials and pulling things apart, cleaning membranes, looking at the data and analysing systems and so on. So it gives you a really good training ground. So students would come through R&D. Quite often we would recruit the best of the students. They'd see what we do, and more often than not, the best students wanted to work with Memtech. And so we could capture some of the top students coming through the university, give them this great training in R&D, and then often send them off to other parts of the business. And that became a significant feeder for good people to run technology opportunities for us throughout the company.
So who were some of the graduates we might know?
Well, Troy Walker is one. I think he's still around in the US doing very well. There's probably a number of others.
Mark Thompson.
Thompson.
Greg was a student. Greg Leslie was a student at one point, working in R&D.
So he came through R&D as well.
Who's now a professor back at the university and running a UNESCO Membrane Science Centre, right?
I think the other thing is that even outside of MEMCOR, if you talk to a number of the prominent consulting engineers, some of them cut their teeth in terms of their membrane expertise on MEMCOR projects. So we gave not only our people a significant learning experience, but also some of the, we had to, Jim Legier, the New Zealand decided to copy the surface water treatment rule in concept in terms of their regulatory framework for water. Jim, through the Association of Becker Engineers with CH Tuam Hill, spent a lot of time supporting the Joyce Road project, which was the first major drinking water plant in New Zealand using membrane technology. I think that there are loads of other examples of that sort of thing that happened.
I mentioned Mark Fabig worked with
you,
and then he built Osmoflow and with Annie.
His first job as a graduate was with MEMCOR for nearly 3.5 years.
And I should credit Bill Beck, the then R&D manager, for his insight into getting those programs set up. And I think it was the R&D team in particular were quite a strong sponsor for those students for many, many years. Yeah.
And today, Warren, you're doing some interesting work applying some of the same concepts on a interesting and unique kind of scale, right?
Yeah, it's interesting how my career took a bit of a turn. I'd back in 2009, I was the R&D director for MEMCOR products, and I had an opportunity come up. Dennis Hanley contacted me, and he was looking to start up a little company doing solar research, and some ideas that a couple of guys who are ex-Memtech employees actually came up with. So that was it came at a time when I felt like I was looking for something new, and went off and did that for a while. Probably not relevant to this discussion, but we ended up making some good progress, but deciding to just park that for a while we could think about better opportunities for raising capital down the track. But I came back to the water industry, and I came across a little company that turns out we're only half an hour from my home, called Aquacell, and I contacted them there. I read that they were doing some work in MBR, contacted the owner, Colin, and he told me he was doing a project using these MBR modules from MEMCOR. And I said, well, I know a thing or two about those, so maybe I can help. So I ended up working for them initially as a consultant, and then staying on as their technical manager. So we've been doing a lot of projects with our partner organisation, Phoenix Process Equipment in the US, and doing a lot of small-scale recycled water systems in buildings and commercial offices. So we did some projects, for example, with Facebook on their campus at Menlo Park. Did a black water recycling system for them, and we're doing one at the moment in Salesforce Tower in downtown San Francisco. So we probably have something like 30 of these small-scale MBR systems on grey water and black water reuse schemes throughout.
Like decentralized, right?
Decentralized systems, yeah. But the interesting thing is that the majority of them are in San Francisco itself. And this takes me back to sort of one of the points we made earlier. The reason there are so many of these little projects in San Francisco is that there's a regulatory driver. Right. The city of San Francisco decided to mandate water recycling systems in any new development over 100,000 square feet currently. And so that created the opportunity for these kind of little projects to get off the ground. And when you look back at the history of Memtech, I think things like the surface water treatment rule were significant milestones in the acceptance of the technology and taking a step forward, because it helps you overcome that sort of cost barrier, and you have to have that sort of added driver, right, which helps to make it happen. And in this case, that regulation meant that people were forced to look at water recycling And as it happens, the technology that Aquacell has, which is mostly MBR systems coupled with RO or sometimes with ozone and chlorination and UV and the like, fits neatly into that. There's some unique features to what you do when you're doing an in-building system versus some of the larger projects that DuPont are currently doing. But the concepts are very similar, but it's all scaled down, and it makes it quite challenging.
All right. So anyway, unfortunately, I think we've come to the end of the allotted time. I'd like to really congratulate you on the careers that you've had, the work that you've done, and thank you for coming all the way from Australia to participate in this chat with pioneers, and it's been really interesting, and I hope you enjoyed the rest of your time here.
Thank you, John.
Thank you, John.
Thanks.
It's a pleasure.
Pleasure.